Hello and welcome to this video. We are going to be solving our POTD. So here we have ancestors in a binary tree. Let's quickly read the problem statement. Well, it says, given a binary tree and a target key, you need to find all the ancestors of the given target. All right, quite simple. And there's also a note. It says the height of the tree is h, all right, and the space is used implicitly for recursion stack. Fine. So let's take a few sample cases and see what actually is the question demanding. Here, let's say we have this binary tree and the target that we are given is 2. Fine. So in this case, where we only have these three nodes, we can clearly see that 2 only has one ancestor. That's 1, right? And that is why we are returning 1 here. Now, if we take another example, this one, a slightly bigger binary tree, and the target now is 7, correct? So here you can see 7 is lying here. Now we need to give all of its ancestors. And the answer says we have to give 4, 2, 1, this one, right? Let's quickly understand this problem. So let me just make this tree here. Here is this tree. Now when I'm talking about ancestors, what I mean is that let's say I'm having 7. All of the nodes that lie between the traversal starting from the root till this target element. Okay, all of the elements that are coming in this path. Fine. So let's say we take 6 as an example. What are all of its ancestors? Beginning from root, root is the ancestor, right? We have then we are going to encounter 3, and then we'll reach 6, right? So in this path, all of the nodes that we have encountered are 1 and 3. So let's see how are we going to approach this problem. Well, when we're talking about uh, trees, we usually just go for recursive approaches, right? And this question is no different. We are going to be finding its answer in a recursive approach. And that means, let's say my target value, that is 7, it's given here. I will start my calls from here, from this root, right? From the root, I will pass on 2 calls for the left and the right. The question I'd be asking is that if I have encountered my key, or you can say target, in the path, then I should record this root. Okay, if this tree has the target, that means 1 is going to be included as an ancestor. Quite simple. Again, let's call the subtree. Now in this subtree, where 2 is going to be acting as a root, we are going to check the same thing, whether my left subtree has the target or not. If it has the target, then I'm going to add 2 to it. If it doesn't, I'm going to avoid adding 2. Fine. Now, there could be 2 situations. 7 can be found or 7 might not be found, right? In that case, we need to figure out what cases are possible. In this case, driving it to the base case, 2 is going to be making call to this 4. 4 will call its subtree. Here the target will match. And here we can return true, a Boolean value. That will let us know that 4 does have like a child, or you can say a subtree, which contains the target. Fine. And we are talking about either of the ways. So my left subtree could also contain my target, or my right subtree could also contain the target. In this case, my right subtree does not contain a target. So for 4, I receive 2 answers. From the left side, I'm receiving true, that okay, target is found. From the right side, I may receive false, that the target is not found. You can see if either of the like subtrees have my target node, the node itself will act as an ancestor, and it will be recorded in the sequence that I am calculating. Fine. Okay. Now, in this case, once we reverse, I also have to say that yes, that this subtree has the target. So this subtree also will return true. Fine. Now, 2 knows that this subtree contains the target. If it does, 2 will be recorded. From this side, from the right call of 2, it will receive false, because we are going to check to 5, then 5 will be checking its left and right, which will encounter null values, and this is our base case. Whenever we encounter null, we will return false. Whenever we find out the value, we return true. Okay. And when we receive two calls for a particular node, we have to take OR of it. So that, what does it mean? If either of the side have my target, that means my work is done. Okay. So I hope the approach is clear to you. Let's quickly take a look at the code of it. So here is the code. As you can see, I received this function and I'm making a list which is called nodes. In this, I will be having all my ancestors. Okay. And I've just made a util function here, utility function here, and I have passed this nodes here. And the main target of this function is to traverse my binary tree and find out the ancestors. Okay, I've sent root, the target value that I need to find, whom ancestors I need to find, and the nodes which will be recording my answer. Okay, here it is. Now, as you can see, the first base case is that whenever I encounter a condition when I'm reaching null or none in case of Python. So whenever I'm reaching at this point, that means my leaf node has ended and I have not encountered my target node in this path. If it is the case, that means the possible answer is going to be false, returning from here, and that is what I'm doing here. The other case could be, the other way around could be, let's say this is 7, that is my target value. So here I'll compare that if my roots data equals to my target value, here it is, so I'll return true. So from these sides, what I'll get false from here, I'll get true from here. Eventual answer that I need to pass on is going to be true because I'm talking about either of these sides, right? And that is what I'm doing here. Let me just clean it up. This chunk. What am I doing? I'm making a call to the left side, to the left subtree. I'm making a call to the right subtree. If either of my subtrees have my have my target value, then what will I do? I'll simply append the root node, okay, the root node's data, and I'll return true from here. If this condition does not occur, I will return false. Okay, this condition will get false only when both the sides are giving me false. Okay, so I hope this is clear to you. Let's quickly have a discussion around the complexity this code is going to take. So when we're talking about this approach, what we are basically doing is we are performing a tree traversal, right? We are going through each and every node in our tree and we are trying to see if my target value is present there or not. And when we are talking about binary tree specifically, we are avoiding no node here, right? We are going to each and every node. So when we are going to each and every node, we are consuming O(n) amount of time, right? In the hope of that we are going to find our target somewhere. All right. Now talking about the space complexity. It is O of h, or you can say O of height. In this case, you can see our height is 4, correct? And in any of the case that you are going to take, if you are having one of the extreme leaf nodes, which is contributing to the height as a target, the possibility the possibility is that you have to record all of the nodes which are coming in this path. Okay, just the leaf node. So you can say it is somewhere OH minus 1, which again is OH, right? So I hope you know that the worst case could be this one. And that is why we are saying that the space complexity is O of H, because we are recording all of these nodes in one list or an array. Okay, let's just try to run this code and try to pass all the test cases. All right, here we are with the same code written. Let me compile and run it. All right, it is giving me the correct output for my first sample case. Let's try to test it against all of the test cases. Okay, so it has passed all of the test cases. So this question was quite simple. And if you know how a binary tree is working, then obviously it is a very easy question for you. And I hope you have understood this approach. You have understood the question now. If you like the approach, if you like the video, do tell me in the comments and press the like button.